Hello everyone, I'm Raghav and we are the Allam Cycle group, the carbon dioxide sequestration by the Allam Cycle. So I want to start off by giving a brief overview of our senior design project. As you can see on the graph, natural gas is the largest source of electricity in the United States and accounts for over 40% of the total electricity industry. Now, when we generate electricity using natural gas, it leads to over 600 million tons of CO2 emissions per year, which increases the threat of climate change and global warming. We must solve this. Our goal is to design 300 megawatt plants, and we do that in three cases. Number one, the natural gas fired combined cycle or the NGCC, which is already used in the industry today. Number two, the NGCC with the CO2 capture or the post-combustion carbon dioxide removal, also known as CDR, and that recovers 90% of the CO2. Number three, the Allam Cycle, which sequesters 99% of CO2, and this is a completely new technology in the chemical engineering industry. We simulated all of this using Aspen Plus and conducted a solid financial analysis. In that, we also included the US tax code 45Q, which means that as part of a carbon capture process, we have access to a certain tax credit or subsidy of $50 per ton of CO2 emitted. We will be operating in regions where we already have existing natural gas and CO2 pipeline infrastructure. For this project, we have chosen that region to be the US Gulf Coast. Now I'm going to popcorn it over to Sarron to explain the NGCC.
This is the process flow diagram for case 1 and case 2 of the NGCC. In both cases, ambient air is compressed and natural gas, which we assume to be 100% methane, is taken at pipeline conditions and also compressed to the same pressure as the compressed air. The compressed air and natural gas are then combusted at constant pressure in the combustion chamber, where we assumed 100% conversion of methane. The gas from the combustion chamber, which is a combination of inert nitrogen, excess oxygen, and the combustion products, carbon dioxide and water, is received by the gas turbine and expanded to produce power that runs the generator. To recover the heat from the exhaust gas leaving the turbine, that gas is passed through a heat recovery steam generator, also known as an HRSG, along with cold pressurized boiler feed water that comes from the pump to produce steam, which is 100% water. The steam is expanded in the steam turbine, which also produces power that runs the generator. The steam is then captured in the condenser to exchange heat with cooling water at constant pressure and create saturated liquid. Finally, the saturated liquid from the condenser enters the pump to be pressurized and is returned back into the HRSG to repeat the cycle. In case 1, the flue gas leaving the HRSG exits directly into the atmosphere. However, in order to make a better comparison between the NGCC and the Allam cycle, we decided to add a post-combustion capture technology in case 2 to capture the carbon dioxide from the flue gas. An amine scrubbing unit is what's typically added, and it captures 90% of CO2 at 99% purity. The CO2-rich stream that exits the amine unit is then compressed to pipeline conditions for transport, and the other stream leaving the amine unit is released into the atmosphere. For our equipment design, we combine the air compression, combustion, and expansion steps into one unit. This is what's typically done in industry, so we modeled our process with a GE F-class turbine. As seen in the diagram, the air is compressed in the cold section and combusted with natural gas that is injected into the hot section. These combustion products are then expanded in that hot section. In industry, the most common HRSG is a horizontal drum, as seen in the first picture to the left. In this configuration, the hot exhaust gas from the turbine flows through the horizontal tubes. We modeled this in the Aspen exchanger design and rating as a shell and tube heat exchanger with the boiler feed water in the shell, and the sketch is shown on the right. The amine scrubbing unit for carbon dioxide removal was not rigorously modeled. However, the capital and power requirements are well documented in the literature for the standard CDR system shown below. The process relies on CO2 absorption and then a solvent stripping tower. Standard amine scrubbing units are capable of recovering 90% of CO2, but are costly due to the large amount of flue gas that must be processed. And now I'm going to pass it off to Eric, who's going to go over the Allam cycle.
So as Ron mentioned, the two primary economic and energy costs for post-combustion capture are the large amount of flue gas that must be processed and compression of carbon dioxide to a pipeline from near ambient conditions. The Allam cycle seeks to mitigate both of these costs by separating the oxygen and nitrogen before combustion and utilizing a supercritical carbon dioxide working fluid, which can be purged at pipeline conditions and purity. In order to do this, we need two large processes at once. The first is an air separation unit shown in the top half right here. Air is compressed in the main air compressor, and a fraction is compressed further in the booster air compressor. Both of these compressors are multi-stage compressors, and the interstage cooling streams are used for heat integration in the Allam cycle below. The compressed air enters the cryogenic heat exchanger and is brought to cryogenic temperatures using the products from the distillation columns. After being cooled to cryogenic temperatures, the oxygen and nitrogen are separated in two separate columns. The high purity oxygen is in liquid form and is pumped to the specifications in the Allam cycle. It is then boiled in the cryogenic heat exchanger. The high purity nitrogen exits the cryogenic heat exchanger and can be sold if a customer is nearby. The high purity oxygen is then fed to the Allam cycle and mixed with a fraction of the supercritical carbon dioxide. Both streams are then pumped, preheated from the ASU, and then heated with the gas turbine exhaust and fed to the combustor. Also fed to the combustor is natural gas, which is compressed from a pipeline feed. The high temperature, high pressure gas produces power in a gas turbine, is cooled in the recuperator, and then it is cooled further before being fed to the separator. Since nitrogen was removed before combustion, we only have to separate the CO2 and the water. Using a flash vessel, the CO2 vapor leaves the top and water leaves as a liquid in the bottom. The CO2 vapor is compressed to pipeline specification, and about 3% is purged in balance with the additional CO2 produced in the combustion. The 97% recycled is to moderate the flame temperature in the combustor, and the 3% leaving is at pipeline specification and purity, and we're recovering over 99% of the carbon dioxide. The major equipment in the ASU is the cryogenic heat exchanger, which is a brazed aluminum plate fan heat exchanger, shown here on the outside, with a warm and cold fluid alternate flows between these plates to increase the surface area for heat exchange. The two columns are aluminum cryogenic distillation columns with structured packing which increase the contact area for separation. They're insulated in a large cold box shown here to keep at the cryogenic temperatures. In the Allam cycle, a diffuser style barrel pump is used to reach combustion pressures. These two pumps can go up to 16 stages and produce pressures up to 4,500 psi. Lastly, the recuperator is what's known as a printed circuit heat exchanger from Heatrick. The outside of it is shown here, and the inside with the circuit design where hot and cold fluid alternate is shown in the bottom picture right here.
All right, everyone. So now I want to focus on the financial analysis. As you can see, the net present value of the Allam cycle is lower than that of the NGCC with and without the CDR. While the cash flow is largest in a typical operating year for the Allam cycle, because of the CO2 tax credit, over 20 years of operation, this is not enough to offset the larger outflow which is made in the first year of construction, which is about $863 million. Now, what can be done to make the Allam cycle more attractive? The answer lies in US tax code 45Q. That should increase from $50 per ton to $112 per ton to financially break even with the traditional NGCC, and to $163 per ton to yield an internal rate of return of 15%. These break-even credits are in fact lower than the NGCC with CDR, since we have increasingly higher returns with 99% CO2 recovery.
To conclude, we first simulated 3 power plants in Aspen Plus, then calculated capital expenditure through equipment design and costing. We then conducted a cash flow analysis in 3 primary markets. And through our results, the Allam cycle is able to capture over 99% of carbon dioxide, compared to roughly 90% in NGCC with CDR. While it is less economical under the current tax code, because it's able to capture more carbon dioxide, it has increasingly better returns as the CO2 capture rate goes up. Given both the increasing threat of climate change and US funds for carbon removal projects, we feel the Allam cycle has potential to play a role in climate change in lowering the over 600 million tons of carbon dioxide emitted from natural gas power plants.